Well, it's time to start our new topic, and this time we're going to be looking at the mole. So we looked at this the other day briefly in class with an introductory activity where we were looking at the fact that the mole is just a scaling factor. It's a word we use for a big number, much the same as what we do for a dozen or something like that. So let's have a look at it in a little bit more detail. So, okay, let's have a look. The mole is given the symbol little n, okay? So anytime in a chemistry equation where you see the symbol with the small case, lowercase n, that is going to mean the mole of substance or the amount of substance in mole, okay? So its units are mole, M-O-L, without the E on it, okay? And so anytime we see this, so we might see there's a number of equations that we will see and we'll come into contact with over the course of the next year, but little n in chemistry is always the number of mole and it has the unit MOL. So the mole itself is derived from the Latin word for mass, okay? And essentially it's a counting system for very large numbers. So it's a unit of measurement, and those very large numbers are 6.02 times 10 to the 23, okay? So remember, if one dozen was equal to 12, well, 1 mole is equal to 6.02 times 10 to the 23. Okay, so at this point, it's just a name we use for a large number of things. So essentially, it works as a scaling factor. So atoms are really, really small, and there's so many of them that we can't count them individually. We need to be able to move from the atomic level, where we're dealing with the number of atoms or molecules in an equation, up to the practical level where we can physically weigh this kind of substance out, okay? So if we look at the equation, say, for making sodium chloride, where we have sodium metal reacting with chlorine gas to give us NaCl solid, and in this case we will have 2 here and 2 here, okay? What we can say is that 2 atoms of sodium react with 1 molecule of chlorine to give us 2 equivalents of sodium chloride. But if I wanted to do this in a lab, I can't measure out 2 sodium or 1 chlorine. I need to be able to go from counting atoms or individual molecules to weighing out in grams, the kind of scale that we can actually physically handle in a lab. And the mole allows us to do that by providing a scaling factor that will relate the number of particles back to the mass of the substance. Okay, so in the way that we can have a dozen bread rolls or a dozen eggs or anything else like this, we can have a mole of any substance, okay? And it is defined as the amount of any substance that contains as many particles as there are in 12 grams of carbon-12. Hopefully you'll remember we've seen this idea before of 12 grams of carbon-12, and that was what we saw with the relative atomic mass when we were talking about isotopes, okay? So we talked about the fact that we gave carbon a mass, relative atomic mass of 12, based on it having 6 protons and 6 neutrons, so 12 atomic mass units. And then the mole was later defined as being the number of atoms in 12 grams of pure carbon-12. Okay, but we can have a mole of anything. We don't just have to have a mole of carbon. We can have a mole of oxygen atoms. We can have a mole of ions. We can have a mole of molecules, or anything at all. What we need to make sure of is we always define and check what the question is asking us in terms of which particle we're actually counting. So this rather scary looking guy here is Amedeo Avogadro, who the constant is named after. Okay, so the mole is named after Amedeo Avogadro as Avogadro's constant. It is given the symbol a capital N with a little subscript A, or in your data booklet and sometimes in the IB is given the symbol L. Okay, these are the same thing, they're just slightly different symbols for exactly the same value, and that value is given in particles per mole. Now remembering that this can change, okay? It's whatever particle we happen to be counting. Ions, atoms, fleas, it doesn't matter. Whatever we're counting, it is the unit particles per mole. So it might be the number of oxygen atoms per mole or the number of sulfate ions per mole of copper sulfate, okay? But we define the particle and then give it the per mole notation after that. So it was determined experimentally, okay? So it's an empirical measurement, and it was found to contain 6.0226 times 10 to the 23 atoms, okay? But we tend to round this down to about 6.02. Always remember to check the value that's specifically given in your data booklet. So 1 mole of any substance contains 6.02 times 10 to the 23 things, okay? There's a video here that you can go on and watch which talks about the mole and how it was derived. So please take some time to have a look at that after you've watched this one. Okay. Oops, sorry. There we go. Mole. So it's just a counting unit like a dozen. So you don't want to be freaking out because the numbers are large. You just need to remember that you know how to deal with things like a dozen, okay? We have a dozen cars, those kinds of things. Now we're just using it in the same kind of way. So we can say that 1 mole of hydrogen atoms would contain 6.02 times 10 to the 23 hydrogen atoms, okay? But this is just straight hydrogen, not H2, okay? So that would just be hydrogen atoms on their own, whereas hydrogen molecules, which are 2 hydrogen atoms, okay, H2 bonded together, it would be 1 mole of hydrogen molecules would actually contain 2 mole of hydrogen atoms, okay? 1 mole of water molecules contains 6.02 times 10 to the 23 water molecules, and if we think about this now, it's got an oxygen and 2 hydrogens. So if I had 1 mole of this whole thing, I would have 1 mole of oxygen atoms, and I would have 2 mole of hydrogen atoms, okay? It all matters about what we're counting, okay? So whereas 1 mole of water molecules, okay, 6.02 times 10 to the 23 water molecules, I would have 1 mole of oxygen atoms and 2 mole of hydrogen atoms. We've just got to define where we're counting from, okay? So if we had 1 mole of each of mercury, zinc, silicon, aluminium, sulfur, and bromine, they would all have the same number of particles, but they wouldn't weigh the same. The mass would be different for each of these different samples. Okay, and if we think about that, that makes sense because it should be, because each of the atoms weighs a different amount. Okay, if I had 1 dozen eggs, say, that weighed 50 grams each. So if it weighed 50 grams each, then I would have a total mass, 50 grams each. Then the mass of that total dozen would be 50 times 12, okay? But if my eggs weighed 70 grams each, it would now be 70 times 12. So if you think about it, each one, so this is mercury, and then we've got zinc, this will be silicon, aluminium, sulfur, and bromine. These all have different relative atomic masses. So it would be the relative atomic mass multiplied by 6.02 times 10 to the 23, and that would be equal the mass that was in each sample. So because the atoms weigh a different amount, we would have a different amount of mass in each sample, even though they all have the same number of particles. Okay, so just remember, it doesn't matter what we're counting, 1 mole will always equal 6.02 times 10 to the 23 things, and in this case, it would be apples. So always just relate back to your question. Okay, so it's a large number. It provides a link between the theoretical work and the practical work. So if we look at the atomic scale here for making carbon dioxide, 1 atom of carbon with 1 molecule of oxygen will give 1 molecule of CO2. So now I can say, if I use a scaling factor where 1 mole okay, of each of these, I can say that 1 mole of carbon would react with 1 mole of oxygen to provide 1 mole of carbon dioxide. And you'll notice each time here it's 1 mole of carbon atoms. In this case it's 1 mole of oxygen molecules and 1 mole of carbon dioxide molecules, always specifying the particle that we're counting. Okay, now if we actually take this and go, well, we know that 1 mole of carbon is 12 grams. So we can say that 12 grams of carbon will react with 32 grams, which happens to be the mass of 1 mole of oxygen, and 44 grams of carbon dioxide will be produced. So we can see here that we're linking this idea of how many particles to an actual mass. Okay, and we do that by going through our relative atomic mass, which we will look at shortly. Okay, so 1 mole of carbon dioxide molecules will of course contain 3 mole of atoms because it's made up of 3 different atoms. Okay, it's made up of 2 oxygen atoms and 1 carbon atom. So for each mole of this, it's made up of 3 parts. I will have 3 mole of atoms. So we can relate this back to our relative atomic mass, which we did previously. We managed to show that in grams, but essentially if we had 1 carbon atom with a mass of 12 units being its relative atomic mass, and 12 hydrogen atoms with a mass of 1 unit each, its relative atomic mass is going to be 1. Okay, remembering that every mass was based relative to carbon 12. Okay, this means that we can now read our relative atomic masses off our periodic table and treat them as the same as mass of 1 mole. Okay, because carbon 12 was based off, the periodic table was based off carbon 12 and the mole was based off carbon 12, that now means that the relative atomic masses on the periodic table, okay, are also equal to the molar masses. Okay, which is essentially the mass of 1 mole. Okay, so we know that carbon has a relative atomic mass of 12, so it will be 12 grams per mole. We know that oxygen has a relative atomic mass of 16.01, and it will be 16.01 grams per mole. Okay, which means O2 will be 32.02 grams per mole. In the same way as we added up for relative atomic mass, we can now add up for molar mass. Okay, so let's have a look at our very last one here, where we're looking at how we structure our calculations. So if we are given the mole of substance and we want to know how many particles, we simply multiply by 6.02 times 10 to the 23. Or if we're given the number of particles, we simply divide by 6.02 times 10 to the 23. If we put this relationship into a formula, we will get that the number of particles is equal to the number of mole multiplied by Avogadro's number. Or, because it's handy to know formulas for the number of mole, we can rewrite that as little n is equal to big N over NA. And that gives us our formula. So this is the first formula for the number of mole that you need to memorize. Okay, so write this on your formula sheet and we will practice some of these calculations in our next video.